Hello class, and welcome back to Calculus. This is lecture 31 on vector fields. As a pre-reminder, I made myself a little note to remember to do this. There is a day of class that we're skipping because of the schedule change. So we lost 3 days, I reset the schedule, and then we got 2 days back. And so we ended up skipping a day, and the materials in the textbook covering computations and interpretations of integrals. And so this is where the textbook talks about thinking the mass of objects where the density depends on a function and integrating to get mass instead of integrating to get volume, and how to compute centers of mass and moments of inertia. These are all topics that would come up in a physics mechanics class, a calculus-based mechanics class, physics 1 sort of thing. And we're skipping them. They're important to see, and so I'm leaving them in the textbook, and I encourage everyone to do those sections of the textbook. But we're not going to test on the physical applications and interpretations, so we're not going to be asking any questions, I mean, obviously on exam 3 that you've all seen, but also on the final about work or density and mass of objects and computing them using integrals. We are just going to move on, but it is an important thing to have seen once so that when it comes up in a later class, you remember it and you remember that you already know how to do all the calculus involved. And the only hard thing is setting up the integrals that you care about. But today we're talking about vector fields, which is our new big topic. And first up, I want to give a recommendation. And so today's recommendation is an artist from Australia called Stella Donnelly, and she has this amazing album called Beware of the Dogs. She's a great singer-songwriter with a fantastic voice. She writes really fun lyrics, and they're mostly about toxic masculinity and how she has, suffered through lots of bad relationships and, very anti-patriarchy. I went and saw Stella Donnelly this last year in concert when she came through Columbus, and it was one of the best concerts I've ever been to. It was amazing. She's really, really fantastically entertaining. So highly recommend the album. It's a real treat. And so today we're talking about vector fields. So I've given a couple answers here in the form of pictures, and the question is, what is a vector field? And my favorite answer is hedgehogs are vector fields. Hedgehogs. Because they are covered in hair, and so they're a sphere covered in hair. And that's one type of vector field. Another type of vector field, this is a wind map. I just looked it up just now. It's a map of the current wind trends across America or the continental United States. And you can see, in Columbus right now, it looks like the wind is kind of moving mostly to the east, a little bit south, very small amount south, mostly east, and, it's kind of windy out. Whereas, over here, there's very little wind compared to what's going on across, Montana, where there's lots of wind and it's going north-west. And so you might have seen these sorts of visualizations before for wind currents. Down here, we've got a magnetic field visualized as, this is a classic picture of a magnetic bar being put on top of a glass plate covered with iron filings, and the iron filings line up in agreement with the magnetic field, and they allow you to see the magnetic influence between the North Pole and the South Pole of this magnet. So you end up with these kind of giant flow lines. And this last picture I pulled is a whirlpool. And this too is a vector field because if you're standing at any point in this whirlpool, you can kind of tell me which way is the water flowing and how quickly, and maybe out here it's like very small compared to in here it's like really, really quite fast. And we'll be talking more and more about these types of phenomena. But all of these fall under the big idea of vector fields, and that's what we're going to focus on for literally the rest of the semester. So here's a way to explain what vector fields are. So let's recall the different types of functions we've seen so far. So an example of a function from R to R would be something like e to the x, or sine x, or x squared plus 1. And these are ordinary, single variable functions, a la Calc 1. At the beginning of this semester, we started talking about vectors and then talked about vector-valued functions, and those look like the second case. So these are vector-valued. So that might have been something like maybe you had some p of t, which was given as like t squared, comma sine of t. And that told you how to find the x and y values for a vector, which pointed at the point that the vector value function was describing. We also had this kind of strange example of going from R2 to R3 of parametrized planes. So these looked like L of s comma t, and it was like you had some point, so maybe it was like 0, 1, 0 plus s times some vector plus t times another vector, 0, 0, 1, let's say. And this gave you, a plane where s and t told you how much to move in this direction versus this is your like t direction. And we had these like pictures of the plane being filled out by little parallelograms, which tell you which are all the counts of s and t from your initial point, 0, 1, 0. We also have been studying for a while functions from Rn to R, or R2 or R3 to R, which take many variables, but then take vector input, but output single variable numbers. And so these are just things like x squared y, or e to the xy, or z plus x y squared, and those sorts of things. And we just called these functions, but they're multiple variable functions. And they were pretty complicated, and we had to do a lot of work to understand what their derivatives are, and we came up with gradients and partial derivatives and this whole complicated story. The new thing that we're going to focus on is this last case. And so I want to point out that there's something going on over here with how I'm labeling the different types of functions. So the first option, there was no arrow on top because the output was a scalar. The second one, there is an arrow on top of the function because the output is a vector. It's a vector-valued function. The function takes values in vectors. L, when we were parameterizing planes, this was a vector-valued parameterization, And so it actually does take outputs in vectors over here in R3. So that's why it's vector valued. But f, when we had a multivariable function, these multivariable functions didn't have had scalar output in the same way that the original function little f had scalar output. But now we're going to really step it up. We're going to have vector input and vector output. And we had that for the parameterized plane, but you should almost think of that as a special, weird example of a vector valued function, because we had two different parameters that we were thinking about, each in their own right. These types of vector valued functions, oftentimes going from the same dimension to the same dimension, so this might be from R2 to R2 or R3 to R3, we're going to think about totally differently than those parameterized planes. But likewise, they are vector valued. So I'm giving them a vector on top. And the key thing is these are vector fields. So a vector field is a vector valued function of many variables. And we're going to require it to be from Rn to Rn, where these are the same n. So it has the same dimension of input and output. The great things about vector fields is we already have a perfect example. And so the example we already have is the gradient. So let's say f is a function of x and y. And let's pick one in particular. So let's go with x squared plus y squared. Then the gradient, ff, we said, oh, what is that? That's this vector of fx, so 2x, and fy, 2y. And fx and fy are both individually functions, both of x and y. In this particular case, they don't have any cross-chatter terms. So gradient of f, if you think about it, is actually a map from R2 to R2. And our favorite way to visualize this is as follows. Imagine taking a point in R2, so for instance, 0, 0, and producing the vector at that point. And so the gradient of f at 0, 0 is the vector 0, 0. And so I'm going to visualize that vector by drawing it at 0, 0, which I have done. Here's my x, y plot. Okay, let's give ourselves a couple tick marks so we know how we're doing things. Okay, 1, 1, 2, 2, etc. So let's draw some more. So at 1, 0, the gradient of f at 1, 0, 1 is my x value, becomes 2, 0. And so over here at 1, 0, this point, my vector is this. At 0, comma 1, my gradient is at 0, 2. So here, I'm at this vector. And if you also check at 1, minus 1, comma 0, I'm at minus 2, comma 0. So here, I'm that vector pointing out. And 0, comma minus 1 is 0, minus 2. So you also have this vector here. And let's just fill in a couple more. So let's also do these 4 corners. I would encourage you to pause, fill them in for yourself, maybe fill in a couple more so you get an idea for how this is going to start looking. Here are some additional ones that are maybe nice to fill in. And come back and check in with me. So if you filled all of those suggested dots in, you might have come up with some picture like this. And just to point out, kind of as you're moving farther away from the origin, these vectors are getting much, much bigger because they're scaling, their magnitude is scaling with x and y. So for instance, at like this point here, we're actually at a vector whose length is 4. 1, 2, 3, 4. It's like roughly down there. So, and I've drawn most of these as going kind of off the scale as you go out because I ran out of space. Oftentimes when you're doing, when you're graphically trying to understand these sorts of pictures, which are called vector fields, or the vector field plot of the gradient of f in this case, we scale down the magnitude of all of the vectors so that they're all much, much shorter. And then this one might look like at the origin it's here, and if you make them all unit length, you're going to end up with something kind of like this, where they're all radially expanding out. So if you just force all the vectors that aren't the 0 vector to be length 1, you're going to get something where they all point directly away from the origin. And the perfectionist in me says I'm basically done now, so that looks good. Let's establish a little bit of notation. So this is going to be, I'm going to say Cn A to B. This is the n times differentiable, oops, functions A to B. So, for example, C0 functions, we're going to allow 0 to be the following from R to R, are just continuous real valued functions. C1, R to R, these are differentiable functions. Whose derivatives are continuous. And same, you can define C2, R, R, and maybe we can go R2 to R2. These would be twice differentiable functions. With respect to both, sorry, that's notation. So with respect to both x and y, by which I mean you've got all partial derivatives. Up to degree 2, and partials, those second partials, are continuous. This is just kind of cumbersome, though. Most of the time what we care about in calculus are the C infinity functions. So the C infinity functions from R to R say these are infinitely differentiable functions. So things like sine of x, e to the x, all polynomials, we're good. Yeah. So when can we? Right, and so the things that we can plug into gradient are things that are C infinity going from Rn to Rn. So infinitely differentiable C functions from Rn to Rn, and you should think that these are the cases we care about are when f is from R2 to R2, or when f is from R3 to R3. Those are the things we really care about. And then, if you take the gradient of f, what you, these are infinitely differentiable functions from R to R. I'm adjusting all of my notes. So where did I just make a mistake? I want these functions to be scalar valued so that I can take a gradient of them. And the same is also true up here. These are twice differentiable functions with respect to both x and y, and take whose second partials are continuous, but that only makes sense if the target is scalars. So the gradient takes infinitely differentiable multivariable functions, so multivariable, and what it produces is a new function, the gradient of f, which goes from, let's say, let's do this in the blue case. So if we went from R2 to R2, the gradient of f is now takes R2 inputs, but also produces R2 outputs. And in the three-dimensional case, the gradient of f would take R3 inputs and produce R3 outputs. And if the function that you start with is infinitely differentiable, then what you are actually producing is a vector field, which is also infinitely differentiable, by which I mean all of the functions that make up the coordinates of the vector field are themselves infinitely differentiable functions. And so this is maybe a picture, big picture, for what sort of inputs and outputs gradient does. What is the gradient really doing is it eats multivariable functions and produces a vector field. And we were kind of subtle about that before, about what exactly the gradient was. Most of the time, we only dealt with the gradient at a particular point when it was, in fact, a vector. So, some things to be on the lookout for when we're talking about vector fields. And I'm going to restrict myself here to R2 vector fields for most of the remainder of the lecture, but we'll talk about R3. Don't you wait, it's just easier to draw things in R2. So these two vector fields are really popular. So just to be clear, what I'm writing here is the vector output. So how you should think about drawing this is you draw a graph in the xy plane. So here's my magical graph. So for, let me copy it. Aha, there we go. Let me draw in blue. For x comma y, and for minus y comma x, I would recommend going through and trying to fill in what these vector fields look like. I would scale all of your magnitudes down by a quarter or so to try to fit them in the graph. Otherwise, they're going to go off the sides. And check back in with me in a second. Boom, there. And it looks kind of like a little explosion. So to be clear, I graphed this at 1/4 scale, so what I'm actually graphing is 1/4 of the vector field x comma y, which by vector multiplication, this is just scalar multiplication, so this is x over 4 comma y over 4. So at a point, and my points, I'm at a 1/1 scale here. So for instance, over here at the point 2 comma 1, my x length should be 2 divided by 4, which is a half, and so it goes to the right by a half. And then it should go up by 1/4, and that, in fact, looks just about correct. And you can see that this is all exploding away from center. This is called a radial vector field. Oftentimes, people will additionally require radial vector fields to be unit length, which we can talk about going forward, but we can also make these unit length everywhere. So rather than having them change scale as they get longer to show that the vectors are longer, you just make all the vectors unit vectors by dividing by their magnitude. And I'll talk about that shortly. But let's also do this minus yx example. So if you've taken a stab at it, you could do that now. But if graphing these is still kind of a mystery to you, let me show you how to do it. Let me do a couple examples by hand. So at 0, 0, I'm at 0, 0. When I'm over here at 1, comma 0, my y coordinate is 0, so I'm at minus 0, comma 1. So 0, comma 1 is the vector going straight up. And what I'm going to actually graph is minus y over 4, x over 4. So instead of going all the way straight up, I'm going to go 1/4 of the length straight up. It's often kind of nice to graph these, with some patterns. So if I keep making the y coordinate 0 of my points, so I'm just checking all the points on the x-axis, then that first coordinate in the vector field is always 0 because y is 0. So that means my vector doesn't point at all in the x direction. It's only pointing up and down. And then its magnitude is determined by its x coordinate. So when you're over here at 0, 2, 2, 0 in the xy plane, the vector you use is 0, 2, but then I'm scaling it by 1/4, so it becomes 0, 1/2. And as you move out, this goes out to 3/4. Here is at 1, so it's actually up at 4. And here it will be at 5/4. So I'm treating this as 1, 2, 3, 4, 5 in my scale. And as we go into the negative x range, you get minus 1/4, minus 2/4, minus 3/4, minus 1. So you can already see this is not radial. It's not exploding from the origin in the way that the left one is. So this is a totally different beast. Let's also graph in the y-axis. So when we're on the y-axis, the x component of the x coordinate is 0 in x comma y, which means that in our vector field, this second thing will be 0, but the first will be non-zero, which means that the vector is pointing nothing up and down, nothing in the y component, but all in the x component. So when I'm at 0, 1, my vector is minus 1, 0. So it's pointing to the left, but then I'm also going to scale by 1/4. Scale by 1/4, so I'm going to make it 1/4 to the left. At 2, it becomes 2/4 in the x direction, 3/4 in the negative x direction, then 4/4 in the negative x direction. And when you go down the negative y's, the negatives cancel, and you get positive 1/4, positive half, positive 3/4, positive 1. And so you can see this is kind of a little pinwheel sort of setup, like it's spinning. And this is going to be an example of a rotational vector field. VF I'm going to use for vector field. So now go try to fill in what's happening at the other components, and maybe do the first quadrant, and then check in with me. So my first quadrant looks something like this, and you can see that this rotation really is happening kind of all throughout. If this is still very bewildering how to fill these in, because the components, you can't go through and plug each one in, but because we already figured out what's happening when y is 0 and when x is 0, and vectors are additive, you can kind of figure out what's happening at one of these points by adding up what's happening at the x-coordinate and at the y-coordinate on the axis. And so this vector is going straight up, and this one's going straight over, so this one needs to go up and over, so it's going to go upright by 1/4 in each direction. And so maybe to highlight that for another one, so to figure out what this guy is doing, you notice that let's highlight these. That this one and this one should be added. So in the x component of my vector is being determined by the value on the y-axis, and so it's over by 1/4, and then it needs to be up by 2/4, so I'm going to end up with a vector kind of like that because of our scale. And so now for this next one, let me go back to blue, it's going to be over 1/4 but up 3/4, over 1/4 up 4/4, and over here at x = 5, we're going to be at +5/4. So hopefully that gives you some sense of how to fill these in. I'm going to just quickly fill in the rest of them, and we'll move on. Ta-da! There is my little graph. So you can see that it is rotational in that it looks kind of like it's spinning, and over, and there's a big difference between these two types of vector fields. I'm just going to point out something, which is that you can also get a rotational vector field by flipping to y minus x. And what that does is that's exactly minus yx. And so if you turn all of these vectors around, because that's what this extra minus sign does, you'll get the vector field flowing in the opposite direction. So y minus x is going to look like it spins this way around the origin instead of this blue vector field that we've looked at above. So let's imagine for a second that we have been given a bunch of vector readings that we know belong to some vector field, and we're trying to identify what's happening locally. So I'm looking specifically at this neighborhood of the point 3, 3 in my x and y axes. And so I've taken tiny micro steps to the left and the right to, I've gone 0.2 left and right in the x direction and 0.1 up and down in the y direction. And I've measured what my vector field is at each of those points. So you could imagine doing this in the real world if maybe you are you have a weather vane, and you notice that there's no wind at 3, 3, but then you take a little micro step in every direction, and your little weather vane is pointing and telling you which direction the wind's blowing. You could produce this sort of chart. And what I like to do is just imagine that that the points that you care about are right at the center of each of these squares, and so I'm just gonna draw right on top of them. So it doesn't quite matter, right? And so if I'm gonna draw the vector field, here's 0. Over here we have to do the vector I, that's to the right. I plus j, that's upright. J is straight up. minus I plus j. The minus I makes it go left. Minus I is straight left. Minus I minus j is down left. Minus j is straight down. I minus j is down right. And so you can see that this looks radial near 3, 3. Sometimes what people like to say when you have these points where everything's flowing away rather than towards it, because towards it could be the reverse radial picture. Radial in versus radial out, is that this blue one is called a source. Ooh, can I spell? Source. Because you imagine it is a place where water is being produced or wind is blowing away from some source. So, there's something producing water that's flowing all away. So maybe this is where you have a fire hydrant broke open and water is pouring out of it. Whereas this red dot here looks more like a sink, which is a place where, like, this might be a drain hole and water is being sucked into it from all of the neighboring, places where there's water. Yeah. And so this looks like a source near 3, 3. Now let's go to the second example, and I made a couple typos in it, so I have erased it, and I'm going to rewrite it. Okay, and now we're going to try drawing it. So the center is at the 0 vector. I've got I, that's to the right, minus I, that's to the left, j, that's straight up, minus j is straight down, and then I minus j is down left, minus I minus j, or sorry, it's down right, down left, j minus I, that's up left, and plus I plus j, that's up right. And so this looks rotational about 3, 3, and it's rotating clockwise. And so you've got either these clockwise or counterclockwise. Rotational curves, or vector fields. Rotational vector fields. Yeah, that's good. And this is one way to describe kind of local behavior of vector fields, is what do you think it looks like near a point. So you should absolutely be looking for these different behaviors to help understand them. So let's deep dive a little bit in about radial vector fields and give a definition. So here are a couple examples of radial vector fields. I've made them a little bit messier, but all of these, and I've included some three-dimensional examples, but all of these are radial. And the key property of a radial vector field is it has to look like this. It takes a vector x as your input, and then its output looks like plus or minus x, whatever it is at that point, divided by the magnitude of x to some number p. So, for instance, this top one is x divided by x, the magnitude squared of the vector. And so you can see that these x squared plus y squared factors, that's this scalar of the magnitude that's adjusting. What being radial tells you is that this vector field at a point x basically just looks like the vector pointing at x, so that's away, and maybe it's scaled up or down. So that's how you're going to get this sort of picture, which we've now seen a whole number of times. then g here, this is minus the vector x divided by the magnitude of x. So that would be with the square root, but it's cubed. And so that one looks like it's pointing in with some scaling. And you should check yourself that this negative is the thing making it go in. And h and j are the same thing, but in 3 coordinates. So this is x divided by magnitude of x squared, and this is minus x divided by what looks like the magnitude of x squared. So magnitude of x to the 4th. And since this first one, h, has no negative sign on it, it's going to be radially pointing out in, just imagine this, though, happening in 3-dimensional space. And so any point you put, so this is like a little explosion, right, where all the arrows are pointing away from the origin, and this one's going in towards 0. Now we're going to get to the real central question about vector fields, which is sometimes vector fields come from gradients, but not always. And we want to know when that is. So what we'll do is we'll say let f Rn to R be a multivariable function, and let g be the gradient of f. Okay, so now g is a vector field. G is called a gradient field if it has this type of description. And f is called the potential. I don't know why I capitalized that. Let's not do that. The potential, or potential function for g. So it's the function whose derivative or whose gradient is g. And just, this is fundamentally the question of antiderivatives, right? If gradients are derivatives, our big question is, when is a vector field a gradient field? So what this is saying is, let's say you have some field f, and I tell you it's actually a gradient field, then what you know is that f is actually, can be written as the gradient of some function, f. Maybe this is bad. Let's just make all the f's g's. All right, so you've got some field you are curious about, h, and I tell you it's actually the gradient of a function f, then what you can basically do now is, like, f is the multivariable, like, antiderivative for h if the gradient is the derivative. And so just like in Calc 2, the problem of finding antiderivatives is hard. Integrals are hard. But it turns out this is easy in 2 dimensions. So there's a theorem. This is known as the Clairaut test. Test, probably named after Clairaut. I don't know. So a 2-dimensional vector field. So a vector field f going from R2 to R2, which we'll write as f of x comma y is, well, it's two-dimensional, so let's write it like this, and it's basically made up of two different functions. A function for its x component, and there's too many x's floating around, so we use m for that, and its function for the y component, we'll use n for that, n of x comma y. So a vector field is a gradient field if and only if, so this is a complete characterization, the following is true. dn dx minus dm dy is 0. And that's it. So just to point out, if f were the gradient, dn dx, so let's put it this way. Here's the end of the theorem statement. So notice, if f is in fact the gradient of some function, and let's use p for that potential function, then f is px comma py, right? And so dn dx, what this Clairaut test is checking is d px flip that around, d of py, n is py, right, dx, minus d of px dy equals 0. That's the same as saying just is pyx equal to pxy. So if your mixed partials are equal to each other, then the vector field can be unwrapped to a gradient field. And essentially checking these two mixed partials agree is the only requirement. And so subtly buried in all of this, we're requiring our vector field to be infinitely differentiable. So we are assuming m and n are both infinitely differentiable. And the key thing is, if they are, then this kind of goes both ways. So if we have a function and all of its partial derivatives exist, then clearly its gradient field satisfies the Clairaut test, and we can check its vector. The gradient field is a gradient field by the Clairaut test. But the crazy thing is, this tells us when other vector fields are gradient fields. Additionally, this quantity, dn dx minus dm dy, it's so useful, and what I'm gonna do is I'm gonna rewrite this, put this equals 0 over here, because this quantity is so useful that I'm gonna define it to be called this weird symbol. So nabla cross f, and this will be called the scalar curl of the vector field f. If this notation is kind of weird, and it is, for just today, treat this like a rote definition, and next time we will, I think next time, later, by next week at the worst, we're going to talk about why this is a cross product. And maybe another way to remember it, but we need to go up into 3 dimensions to really make sense of what a cross product is. So here we're calling this the scalar curl, because it's a scalar number. So let's work a couple examples. The same question for all of these holds. Is the field a gradient field? And if so, find the potential function for which this is the gradient. Here's a place to pause and try to work it out. Okay, for each of these, what I will do is compute the scalar curl. So remember the scalar curl, nabla cross f looks like the n component. So the notation I'll use is this is m comma n, and m and n are both functions of x and y. This looks like n dn dx minus dm dy. So you take the y one and you do its x derivative, etc. Right? So in the first one, nabla cross f, scalar curl, is the derivative of y with respect to x is 0, x with respect to y is 0, it's just 0, so this is a gradient field. Okay, and let's just figure out what it has to be. That x had better have come from an x squared over 2, and the y has to come, if I take the y antiderivative with respect to y, it looks like a y squared over 2, and the way I can combine these together to get a function is by adding them. So if you add them, then each one is like a constant term when you take the derivative with respect to the other coordinate, and so they don't interact. And so you can double check that this works out. But first checking Clause's test guarantees that you can actually find this antiderivative. So for the second one, nabla f cross, the scalar curl, so nabla cross f looks like derivative of cosine with respect to x. Derivative of cosine with respect to x is minus sine. And derivative of sine x with respect to y is 0, and that's not equal to 0, so it's just not gradient. So I can guarantee you right now you cannot find a function of x and y, a multivariable function, whose derivative with respect to x is sine x, and whose derivative with respect to y is cosine x. It's just not going to happen. Okay, for part 3, we check the scalar curl, and it looks like minus x to the minus 2 from that one, and 1 from the first coordinate, and this is not 0, so again, it's not gradient. And so we're just guaranteed it's not a gradient function. For problem 4, the scalar curl looks like 1 minus 0, which is again not gradient. For the fifth one, the scalar curl looks like 4x cubed minus 3y squared, and that's not guaranteed to be 0. It has to be 0 everywhere because it's a function, so it's also not gradient. So sad. And for the last one, nabla cross f is 1 minus 1 is 2, which is also not 0. So if you're disappointed that almost all of these were not gradient, you should not be. Most vector fields, the infinitely many most that you're going to write down, are not gradient. If you write down two random functions of x and y, it's probably not a gradient vector field. Gradient vector fields are special. If you want another example of a gradient vector field, you can use the radial one. So pick your favorite radial vector field. So let's say f is x over x squared plus y squared, comma y over x squared plus y squared. Then the scalar curl in this case becomes, well, it's kind of messy, but if I take the derivative with respect to x in the second one, it basically looks like y times x squared plus y squared minus 1. And in that formalism, and y is a constant, becomes minus y x squared plus y squared to the minus 2 times 2x. And the m component looks like x times x squared plus y squared to the minus 1. So I'm going to subtract it. I get minus x squared plus y squared to the minus 2 times 2y. And if you check, both of these look like, so this one's minus 2xy over x squared plus y squared squared. And then I've got minus, and this one is minus 2xy over x squared plus y squared squared. And so those cancel each other, and you get 0. So in particular, let's just find a function whose derivative is this. So what I would do is let's focus on the m component. If I were trying to take an antiderivative of x over x squared plus y squared dx, and so y is a constant, what I would probably want to do is set u to be x squared plus y squared. So du is 2x dx, and then I would get a half integral of 1 over u du. So this looks like the ln, 1/2, the ln of the absolute value of u, so x squared plus y squared, maybe plus constant. And for y, when you do the same argument, you're going to get the same function. And so I'm telling you this function will in fact work as your potential function. And so you can just check, and in fact you can replace these absolute values by parentheses, since x squared plus y squared is always positive. And this works as a potential function. You should notice, though, that 0 is not in our domain, because of course we can't divide by 0 in the radial in this radial vector field. But formula still works. And that's where we'll stop today. See you all next time.